All right, I'd like to welcome everybody to the February 2026 DAS meeting. And I'd like to start off with new members. Do we have anybody who's new to the club? Like to introduce yourself? Say hello. Anybody? I'll check.
This year.
Welcome.
Thank you very much.
Well, we're not doing anymore. Anybody else? It's not focusing. Hold on. There we go. All right, next item on the agenda is our dues. Bob, you want to say something about that real quick?
Yeah, we're getting towards the end of the dues collection process, but we have 141 members that have signed up so far. So thank you for paying your dues. It goes a long way to making the program work. There's a few people that were still trying to get paid up, and so I sent an email out last night. So if you got an email from me last night, that means I still have you as not having paid yet. So we're still collecting dues.
All right, thank you. And then Fred, you want to say something about Friday Night Lights?
Friday Night Lights is June 26th this year. I'll be getting an email out sometime by mid-April or so. And I don't want to get out too early because it tends to get lost in all the noise. But for those of you who have volunteered before, get it on your calendar, June 26th. It's a near full moon. Moonrise is about 6:08 p.m. that night. And the event's over about 9:30, so it won't even be dark yet. So we'll have the moon to share with the public.
What day of the week is that?
Sorry?
What day of the week is that?
It's a Friday. If there's any questions before you get the email out, you can email me at fredworld@verizon.net. That's fredworld@verizon.net.
Yes. All right, next we have an announcement about lunar eclipse. Greg, you want to do that?
Yeah. If you've been watching the news, you saw that there was a solar eclipse today. Unfortunately, mostly penguins were the only ones who saw it because it skimmed the southern part of the globe. But as it goes with eclipses, 2 weeks later, the moon's on the other side, so the shadows fall the other way, and we'll have a lunar eclipse coming up. This one is easier for us to see, as all lunar eclipses are. Anybody on the moon side of the Earth can see the lunar eclipse. The alignment of Delaware this time makes it fall, so our position is just at sunrise. The moon will be going down. So March 3rd, 4:50 a.m., we see the first little bite. I don't put the penumbral parts on here because that's just too hard to see. But you begin to notice a little bite taken out at 4:50 in the morning, just before 5 o'clock. Then it'll hit the full totality at 6:04, but it's continuing to get lower. You got to have a good wide open western view, no houses, no trees. And then the deepest part of the eclipse, the mid part, 6:30, just before moon sets. So I'm going to get in touch with the New Garden Township Park again, where we've done a number of these places where we need a nice wide open western view. So people are going to be willing to get up in the morning early enough to go out and watch. I'll send out a reminder in a couple of weeks, and we'll get out in the cold and watch the park. And what day of the week is that?
What day of the week? 2 weeks from today.
Okay.
Good. Next item, do note that this May, typically we have our May dinner meeting, but this year we're not going to do that because we're preparing for our 70th anniversary in November. But we would like to thank Jeff for all the hard work he's put in with his folks for all these years running our dinner meetings.
Very good.
Yeah. Unfortunately, he can't do that anymore, but next year we'll make some plans and have a different kind of dinner meeting. We'll think about that over the next year or so, but we do want to celebrate our 70th anniversary in November. And so we want to start preparing for that. Please note that I've been collecting photos and other documents that we can scan and put in a folder for memorabilia and to share among the club and stuff like that. So if you have any old photos, be sure to bring those in. I'll be doing that mainly during like the late spring and summer. But if you want to bring some of that in, we can start collecting that. I already have a bunch of things that the club collected in the past, but if you have some stuff you'd like to share, I'll start collecting that in that folder in addition to that. We do have a Google Workspace folder that is fairly big and is specifically named it DIS Photos. So I'd like to collect some more in there. In related news, I'm wearing our DIS t-shirts from 10 years ago. Did hold up very, very well. Yeah, if you can turn that up, that'd be great. And you can see, still works great. I've worn it to many DIS events, but on the back it says 60th anniversary, which is not gonna work anymore, right? So we got to think about getting the 70th anniversary shirt together. So we are thinking about trying to get like group orders or posting like a marketplace link or a website that we can embed into our website, like a web page with like a sales center or something on our website. There are various ways to do that, but we are not t-shirt experts, and we bet there are some people in this club who have done this before. So if you have experience with any of these online t-shirt web selling services or merchandising that we can do on our website where people could just go on and make an order from our website, then please share that with us so that we can set that up for the club. Because I think that would be better than what we've done in the past with something like Vistaprint where we make a group order. It'd be better if people just say, I want to buy a t-shirt, so they want to do it. So that's what we'd like to try to set up. So if anybody has experience with that, let us know.
Or if you don't have experience but have a willingness or interest to investigate it, you know, all good too.
True.
We still have the DAS hats.
That'd be nice if we did. I don't know.
One,
Uh-huh,
but you don't have them anymore.
I mean, we're gonna have to figure out how to order that stuff again.
Okay.
yeah.
We'd like to, again, make a link or an embedded web page on our website so people can order it, because that makes things simpler.
Mhm.
So somebody knows the best way to do that, let us know, and we can go with that service. I know there are numerous services out there, but no experience with them, so I don't know which one's best. All right, so next item on the agenda, do we have Bill Hannigan for the AP SIG anywhere? Haven't seen him.
I'll see, yeah.
All right, for the book club, Mary?
Good evening, everyone.
Yeah.
I would like to invite the DAS members and their guests to our February meeting. It will be held on Thursday, February the 26th at 7 p.m. via Zoom. The meeting will be led by Diane Turnshek, who is a DAS member, a special lecturer from Carnegie Mellon, and a leader in the dark sky conservation community. We will be joined by two authors, Jarima Osofsky, who wrote Moon Garden, A Guide to Creating an Evening Oasis, and Leanne Henyon, who is the author of Night Magic, Adventures Among Glowworms, Moon Gardens, and Other Marvels of the Dark Sky. In addition, Karen Maxwell, the horticulture director of the Edison and Ford Winter Estates, which boasts a beautiful moon garden, will be joining us. And in addition, we will be joined by Erin Ahern, who is a Skyline Middle School, Delaware science teacher. And she will be joining us to discuss Delaware's Artemis I moon tree, which is a loblolly pine grown from seeds that orbited the moon aboard NASA's 2022 Artemis I mission. So it's a tribute to the Artemis mission. We'll have a statement from NASA to share with attendees at the meeting. And it's also a promotion for dark sky conservation, for planting plants that attract nocturnal pollinators, which is very important to our ecology. And we'll also be joined by a professor from Delaware State, Chris Heckscher, who rediscovered the Bethany Beach firefly, which is on the endangered species list. So we've got public and private gardeners from across the state who will be joining us, including members of the Delaware Federation of Garden Clubs. So if you can't attend the meeting for whatever reason, please feel free to share the invitation with anyone who is interested in ecology, dark sky conservation, and gardening.
Very good. All right, I think that's all that's on my list. All right, Jeff, you may continue with the next part of the program.
We have a couple outreach events coming up,
Oh,
Rob.
I'm sorry.
Thank you, Jim.
Sorry. Yes, by all means.
Okay,
Good enough.
not a problem. Next week, we have an outreach event that is going to be spearheaded by Greg Lee. It's an annual event that we do with the Wilmington Friends School. It's called Night Lab, and it's just off of Kennett Pike, just into Pennsylvania, just after the Delaware Pennsylvania border. It's at a private residence, and Greg Lee will explain more of the particulars about that event. The second event we have is basically a homeschool event that's been spearheaded by Jeff Lawrence. This is going to be taking place in Townsend on Thursday, February 26th from 6:30 to 7:30. And like I said, it's a homeschool event. It appears to be at a private residence on a farm, a lot of open area to set up telescopes, and Jeff will talk a little bit about that also. So, Greg, Jeff.
Well, yeah, I sent out an email and everybody responded real nicely. So we're well staffed for the event, the annual event for the Wilmington Friends School 7th grade science class. Surprising, there are very few science classes that have an astronomy unit any longer, but this school still does. And so we've been supporting that event for coming close to 30 years now. So thank you for the volunteers. I can always use a couple more. So if anybody else it's in the email, send me a note and I'll give you all the details of how to find the spot. Cool. Thanks.
Cool. And yeah, my event with the homeschool group, again, it's going to be younger kids. I know we tend to have a lot of events like up in Wilmington. So it's nice to offer something in the Middletown, Townsend area for folks that might live around there. I know we have a lot of members that live down that way. Naturally, welcome help from anybody. It is at a private residence. I'm not going to broadcast the exact address to everybody, but for those that volunteer, I will give the specific details. I've put one note out already to the groups.io, and I will be putting a follow-up. Looks like it could be a pretty good sized group, so we could use a number of scopes. So keep your eyes open for that one. Thanks, Jim.
Very nice. Now we'll transition to the next one.
All right. So we have one little quickie. A month or so back, Lynn shared a couple of photos, and we had a little bit of a technical hiccup in that one of her photos was missing. So we'll cover that, and then we'll move over to our Lynn. Do you see the one you want to share?
It's in the folder. It's in that folder, the 2005 folder that we did before.
Images 12, 24, 25? Okay.
There should be. What is that?
Are we sharing it?
Are we, Rob?
Yeah, probably not.
Okay.
Okay.
Didn't change.
One of these days I'll remember. There we go. And it's this one. Yeah.
Yep, that's good. And you
And we'll
want to
do-
continue first.
Pin this and then pilot and then she's in there somewhere. There we go.
Okay.
Yep.
For those who got the calendar, look at the picture that you have for January. no, that's not, I asked Wayne if that was his. He said, no. But this is the one that he took, and I went and looked at it, oh my God, it's the exact same picture they've got for January, so. That was the one that got left off. Thank you.
Yeah,
Okay.
thank you, Lynn. That is something. Okay, that leads us to our main talk for night. We are joined tonight by Bruce Ruggeri. He is a career research oncologist who's had decades of interest and passion in astronomy, has been a member of numerous organizations over the years. Closest to home is he's been a member of our friends to the north, not the Canadians, but the CCAS, the Chester County Astronomy Club. So Bruce has been involved with them for quite some time. And the biggest reason for him here tonight is he is a recent addition to the NASA Ambassador Program. So that's really awesome. So yeah, in fact, next month or the month after, I forget, we have John Conrad, who is our other NASA ambassador. So it's a really, really cool program that we get to stay on the forefront of what's happening, in NASA ongoings and all that stuff. So yeah, please, everybody, welcome Bruce, who's going to be talking about the Europa Clipper mission.
So thanks very much, everyone. It's a pleasure to be here. And kind of coincidentally, today is my first anniversary as an NASA Solar System ambassador. So I hope you'll be kind. So what I want to do in about the next hour, if you're all awake, I want to talk about several things in this talk, okay? The first is the whole concept of habitability in our solar system, or more broadly in our near universe. And what are some of those parameters? What does that mean? What do we look for? Considerations. Then switch over to what are some potential candidate worlds in our own solar system, each of which could be a presentation of itself. But I'm going to walk through them. And then we'll switch over to Europa and what makes it a very intriguing ancient world that holds great promise in terms of habitability and maybe underscore even some signs of microbial life. And we'll talk about everything we know, what our current models are of Europa, and then switch gears to a technical aspect about the Europa Clipper mission. And this is the most technologically advanced mission that NASA has ever launched as a planetary probe. And I'll explain why, the challenges, the technology, the objectives and the instrument package, and what were the major challenges that engineers and scientists faced in getting a probe to Europa. And then lastly, we'll switch gears away from the science, away from the technology, and talk about all of our probes as essentially ambassadors for humanity and kind of what that means philosophically. And I'll then close with a concluding statement. So this is the best we can get, right?
On the side, on the side of the switch, no, on the side of the switch is a dimmer.
Oh, okay.
There you go, there you go. I mean, yeah, and the other one.
Yeah, you're kind of, the only other thing we can do is that.
Let's leave that off.
Well, how about this? What usually works is if we give a little bit of
Gotta turn it on and.
a little bit of light to the room, and then we'll darken it up. How's that look?
It's cool. All right. So first things first, let's just talk about life as our understanding of life. Life, by definition, that we're going by here is a self-sustaining, self-replicating electrochemical system that's capable of Darwinian evolution through natural selection. When I say life, I mean carbon-based aqueous life. We're not going to think of more exotic lives that could be based on hydrocarbons or silicon or some other, more obscure elements, okay? So this is our standard definition of life. So how could we recognize extraterrestrial life? Well, in our nearest neighborhood, the best candidate, I think many of us would agree, for at least extinct life is Mars. As you probably know, in the past, Mars was much warmer, wetter than it currently is. It had a stable magnetic field. It had a stable atmosphere, okay? The geology supports all this with riverbeds, lake basins, alluvial fans, etc., that suggest water flowed and perhaps life existed. So the best evidence that we have thus far, and many of you may be aware of this, is that the Curiosity probe last year found organic signatures in a number of locations on Mars. Perseverance at the end of last year, and then they released peer-reviewed results in September of 2025, also identified organic signatures in the Chevyeva Falls in Jericho Crater. Okay, and along with those organic signatures, which were mainly fatty acids and some carboxylic acid or carboxylic acid intermediates, they found what are known as leopard spots. And I'm sure most of you heard of this in the public media. And leopard spots are a very characteristic feature of microbial life on Earth that exists in lake beds or riverbeds, okay? And what these leopard spots are, and the analysis showed, they are iron phosphate residues, most likely vivianite, and iron sulfide residues, most likely greagonite, that are formed from oxidative reduction reactions of organic substrates. So these essentially are microbial waste products, at least on Earth. So Perseverance, with its capabilities, ruled out essentially all of the abiotic processes that could produce these features. There are some, but they ruled out 99%. That's not conclusive that this is evidence of life, but it's pretty compelling and intriguing. In addition, the beds where these rocks were signatures were found are about 2 to 3 billion years old. That extends the so-called habitability window. Most astrobiologists believe that if Mars did ever have life, it was maybe closer to 3.5 or 4 billion years. So this is extending that much longer. Now, unfortunately, the problem is we are now at the limits of what this, technology can do. Okay, we simply can't go any further in understanding whether these are truly signs of extinct life or not, unless we take the samples from this mission, from Curiosity, elsewhere on the planet, and send them back to Earth. That's the dilemma we currently face. Now, this is extinct life. I'm a realist. However, there is a non-zero probability that there could be existing microbial life on Mars, and I'll explain why elsewhere. Remember, Mars is in the habitable zone of the sun, or on the outer edge. Mars has enormous quantities of subsurface ice, not just at its poles, but its terrestrial, equatorial regions, and there are huge volumes of liquid water in the mantle, at least based on what we know. When you consider all these facts, it is not inconceivable that in the subsurface, shielded from the bombardment of cosmic rays because there's no atmosphere, somewhere in the subsurface, in crevasses, in caves, in lava tubes, there could be evidence of microbial life. We just don't know that, but it is a non-zero possibility. So time will tell. Now, if we go beyond Mars, and I wanted to keep this talk to our solar system, but you can't really do that because people ask too many questions about what about elsewhere. It gets obviously much more complicated when we talk about life or the possibility of life beyond our solar system. So in the last 36 years or so, there is well over 6,000 exoplanets that have been identified. Now between TESS, Kepler, Cheops, we keep finding new exoplanets every day. Of those, maybe less than 100, the most conservative estimate, are potentially rocky or terrestrial worlds that exist within the habitable zone of their host star. Most of those are M-class red dwarfs. Some are more sun-like stars. Most are red dwarfs. Now, that doesn't mean they're habitable. It just means they exist in that zone. And if you consider all of this between what we know, the enormous capabilities of James Webb, and now, just in the last decade or so, tremendous advances in high-resolution transmission spectroscopy and what is called high-resolution eclipse mapping, we can look at the spectra in those exoplanetary atmospheres and look for characteristic chemosignatures, in this case, biosignatures. Not one, but pairs or combinations of agents like water, oxygen, ozone, methane, ammonia, carbon dioxide, etc., that all have abiotic origins, but in combination are suggestive of life. Similarly, we can look for cloud and temperature variations in these atmospheres. We can even look for spectra of potential biological pigments that may be produced by small organisms in atmospheres. All of this is relatively new. All of it is intriguing. James Webb has already looked at about 100 such atmospheres with its capabilities. But let's just say, for the sake of argument, we find something really compelling in a biosignature by these methodologies, and it can be confirmed. Well, to confirm that really, to do good science, we obviously need to send a probe. Well, even the best, most advanced robotic probes acting autonomously would take tens of thousands, hundreds of thousands of years to get to a potential exoplanet, okay? Problematic. The problem becomes even more challenging if you were to say, well, let's just look for radio signatures of potential advanced civilizations that may be out there that are trying to contact us or just sending signals. This is not a new idea. It's been done since the early 1960s. We had SETI, laser SETI, cosmic, a relatively low risk venture, depending on your perspective. But let's be honest, you're looking for a needle in a cosmic haystack. Right place in the sky, the right frequencies, right locations. It's a crapshoot. But what if we were to find a signal, confirm that it's non-random, artificially generated? We try to send a signal back. Again, it could take centuries or thousands of years just to send a one-way message. So the point I'm trying to make in all this is we're at the limitations of current and near future technologies and simply the law of physics. Unless in the next century or two, we can go from the theoretical concept of near light speed travel, okay, to a practical model of that without violating relativistic or quantum physics, okay? That's the reality. Now, all this sounds abstract. Let's put it in really concrete terms that I think everybody in this room probably can grasp. Voyager 1, we all know about Voyager 1, right? Launched in September 1977. It is now the furthest man-made object in our universe. 15+ billion miles away, right at the heliopause, right? Where the solar wind is just starting to kind of meet interstellar space. By the end of this year, 49+ years later, November, it will have traveled one light day. One light day. Okay. Now, our nearest solar system, our nearest star system is the Alpha Centauri Proxima Centauri system. Very interesting because Proxima, a red star, has 3 exoplanets. One of them is terrestrial. It's about the mass of the Earth. It lies within this habitable zone of the planet, about 0.05 angstroms from the star, which is a red dwarf. It's probably not habitable, but it's intriguing. 4.2 light years away. For Voyager 1, with almost a 16 billion mile head start, to get to that really interesting system, 4.2 light years, would take 40,000 years. So we have to get grounded in reality and say, all right, where, being practical, can we address this question of habitability or maybe even a search for life within our own solar system using current near future technology, especially capitalizing on the advances made in AI, automation, and robotics. And if you take that approach, as complex as this problem is, you end up with a kind of basic maxim: follow the water. Kind of interesting that not only virtually every major world religion, but every indigenous people on the planet have some proverb that is sort of like this Navajo proverb, Teo Ilina, where water is life, water is self-sustaining. Wherever there is water, life, at least on Earth, finds a way. So if we follow that model, there are certain things that we need to consider. And this feeds in absolutely what I'm going to talk about with Europa and some other moons in our solar system that may be candidates for habitability. Most astrobiologists and biochemists would really say there's 3 main things you need for life. More recent data argues there's really 4. First and foremost, you need water. Okay? You need certain essential elements: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Life as we understand. You need a stable, sustainable energy source. Could be photosynthesis, Could be radioactive decay, could be hydro or geothermal activity, could be tidal frictional heating, as we'll talk about later. And that's usually where they end. But there's another really important component, and this factors into the discussion on Europa, and that is time, stability, the time it takes for the very complex molecular and chemical organic reactions to take place and eventually result in a self-replicating complex molecule. We're not talking about little building blocks or fatty acids or nucleotides or even amino acids, but like big complex molecules, which are just a few steps away in the whole pattern toward the simplest, most basic form of life. That time component is really important. So if we look on light, if we look at Earth, wherever there is water, we find life, no matter extremes of temperature, pH, salinity, osmolality, presence or absence of light, presence or absence of oxygen, even the presence of high degrees of radioactivity, life finds a way. These so-called extremophilic microorganisms are of real interest. I've been interested in for decades from a biomedical standpoint, but astrobiologists use them as case studies for potentially trying to understand life elsewhere, especially in our solar system. Now, multiple times in this talk, I'm always going to raise a caveat. Because these things exist, they not only survive, they thrive in complex ecosystems, doesn't necessarily mean that under similar kind of extreme conditions elsewhere in our solar system, life would be. It's just, this is saying it's possible when the right ingredients are present. So if you follow the premise of go where the water is, you come up with some, I think, pretty shattering kind of revelations. What I'm showing here is data that's been compiled from a number of different craft, from Galileo, Cassini, the New Horizons missions, a number of different sources looking at water in various icy moons of our outer solar system, both the volume of liquid water, the world volume, and the percent. And you come up with a really startling thing, that the majority of water in our solar system is not on Earth. Even though we're 70% by area water, it's not. The big candidates, the best candidates, are a number of these icy moons of the outer solar system for evidence of having subsurface oceans, as well as other kind of geological features that make them attractive candidates for habitability. So the main candidates that we're going to talk about tonight are Europa, Ganymede, and to a lesser extent, Callisto, the Jovian moons, okay? And then two of Saturn's moons, Enceladus and Titan. So these are worlds that clearly are not in our habitable zone of the sun. They are far out. With the exception of Titan, they don't have atmosphere. They have what are called exospheres, very tenuous atmospheres. Many, such as Europa, are bathed in enormous amounts of radiation, as we'll talk about later. And yet, these are our best candidate worlds as to where we might find evidence for habitability, which is then the precursor to possibly being life. Now, my talk is going to be on Europa, but given the nature of this subject matter, I would be really remiss, even though they're whole separate seminars, if I didn't say something about Enceladus and Titan, and it'll fit into this discussion about Europa as well. So, Titan, biggest moon of Saturn, okay, presumed subsurface ocean, about 26% by water. Titan has a hydrocarbon-rich atmosphere, about 1.5 times the pressure of that on Earth. It's believed to be one of the best models in the solar system for a pre-biotic Earth. Earth, before there was oxygen, different set of conditions that may have ultimately given rise to life. You have this thick hydrocarbon atmosphere, a hydrocarbon, probably methane-based precipitation in cloud cycle. You have a surface covered in rugged ice, mostly water, maybe some ammonia, and pools or lakes of liquid methane and ethane that undergo seasonal and tidal fluctuations because of the gravitational effects of Saturn. And you have this subsurface ocean. So this is an intriguing place for early life or origin of life type studies. The other moon, though, that garners a lot of attention is Enceladus. And many would consider this one of the best candidates to look for life. And I'm going to try to make an argument both ways in talking about Europa. So in addition to Voyager, the Cassini mission made 23 flybys, enormous amount of data collected on Enceladus, and we're still looking at that data, we're reevaluating. So what do we know about Enceladus? Well, this is a tiny moon. It's only about 300 miles in diameter. It's the sixth biggest moon of Saturn. It's like 20th in the solar system. It's tiny, it's small, but we know it's geologically active with an icy surface that seems to be undergoing a lot of surface remodeling. It has an ice layer about 12 to 18 miles thick, and most certainly it has a subsurface ocean, okay, that undergoes tidal frictional heating from Saturn and also Saturn's other moon, Dione. Evidence of this geologic activity is in the South Polar region. You have these objects called tiger stripes, and around these tiger stripes, you have evidence of cryovolcanic activity. Water plumes, as well as icy grains and plumes that are sprouting all along this region in the South Pole. And intriguingly, they contain some very interesting molecules. CO2, water, hydrogen, methane, ammonia. And the grains are either water with salts, or many of them are actually water with both simple and initial complex hydrocarbons, which is a big deal, a really big deal. So much of this material is injected that it helps form part of Saturn's E-ring, okay? Hundreds and hundreds of miles into space. We also have, based on evidence from some silica grains in these plumes, that Enceladus probably has hydrothermal vents. I think they also exist on Europa. And I'll show you pictures of that. And those vents are driving some of this cryovolcanic activity and the active surface geology. The surface, this is an artist's conception, but the real pictures from Cassini are pretty similar. You have extensive canyons and grooves, high amount of ice, making it the most reflective body in the solar system. And if you could, Enceladus would be a dynamite place to visit, because you have hundreds of feet of fresh powder constantly, falling on the moon. Only very recently, scientists have begun to reanalyze more of Cassini's data. And they see that, it's not just the South Pole area where there's a lot of underlying geology and heat flow. The North Pole has it as well. And the flow between the North and the Southern hemispheres suggests that they're almost in perfect equilibrium between heat generation and loss, suggesting Enceladus could have a sustained warm ocean that could support life. So you say, well, why the hell are we going to Europa then? Okay. Well, here's the thing. What's key and what's not understood is how old and how stable is this ocean. And this is where things get dicey. 10 years ago, a study came out that said that Enceladus, and in fact, any moons inward from Titan are only about 100 million years old. Well, that's a geological blip in time, right? When you're talking about life. Another study came out a few years later and said, no, Enceladus could be 1 billion years old. Either way, Europa, conservatively, is 1/4 to 40 times older than Enceladus and much more massive. It's been around upwards of 4+ billion years. So Enceladus is certainly an attractive target, the next phase, so to speak, of exploration of the solar system, but it doesn't diminish why we're sending missions to Europa. So this is just, I'm going to close with a slide like this. Really, missions to Europa are really the second wave, looking for habitability in our solar system, the second wave. Already, NASA has approved a flagship mission called Orbital. It'll be the most expensive mission we ever did, just under $5 billion, okay? It will launch in 2038, arrive at around 2050, and this will be both an orbiter that makes analyses of the surface of Enceladus, as well as a lander that will literally drill using robotic autonomous systems called EELs, and looked for biosignatures and even life. Just the end of last year, both the Chinese Space Agency and the Europeans all have set their sights on Enceladus. And now they have mission concepts for both landers and orbiters in conceptual phases for probably missions in the early 2040s. Okay, so a lot of interest in this moon, but right now the first wave are the missions that I'm going to talk about tonight, and that's to the Jovian system and really to 3 Galilean moons. The Europa Clipper mission, which I'll talk about, and again, I'd be remiss if I didn't mention the sister mission, the JUICE mission by the European Space Agency, that's going to Ganymede and Callisto, and to a lesser extent, Europa. So basically what this mission is, this is probably the most complex and sophisticated mission that the Europeans have ever launched as a planetary probe, state-of-the-art instrument package. It was launched in 2023 from French Guiana on an Ariane 5 rocket. It's on its way to get to the Jovian system in 2031 after 8 years of travel and 4 gravity assists. The basic premise of this mission, compared to the one I'm going to talk about in detail, is this is a 2.5-year mission that will do 12 flybys of Ganymede and Callisto and only 2 of Europa. It'll come between maybe 120 to 600 or so miles from the surface of those moons. Now, why is this important? Well, as you're going to see later, Ganymede and Callisto are much, much further removed from Jupiter's punishing radiation fields. By no means is this a low-risk mission, but much further removed from the magnetic fields and the punishing radiation fields compared to Europa. Okay, that's a big difference between JUICE and Clipper. Nonetheless, this has a state-of-the-art instrument package of 11 instruments that are very similar to those on the Europa Clipper. And when it arrives in the Jovian system, it will conduct in-depth in situ and remote sensing of both the surface and the subsurface, primarily of Ganymede and Callisto, looking for various parameters of habitability. So if all goes well, which usually never does, but if all goes well, sometime in the mid-2030s, we should be having an explosion of data from both of these missions that will be very complementary to one another. So we stay tuned. But now let's turn to Europa, okay? And just Europa. So just a reminder, 4 Galilean moons, okay? Callisto further out, heavily cratered, old, maybe has some subsurface water, but not really geologically active. Ganymede, the biggest moon in the solar system, maybe has upwards of 46% water in its subsurface. Also cratered, but again, active tectonics, signs of remodeling. Io, the most volcanically active moon in the solar system, right out of Dante's Inferno. You know, this is not habitability, okay? And then we have Europa that kind of is in a nice sweet spot. So if we look at Europa, it's about 90% the size of our moon. Surface is heavily covered with ice, so it has a high albedo, not as much as Enceladus, but it's pretty reflective. Tidally locked orbit with Jupiter, nearly circular about every 3.5 days. So now you have the second most massive body in the solar system, Jupiter, with a body about the size and mass of our moon. You can just imagine the gravitational, torsional, frictional forces that are ongoing, which we'll get to. We know that this moon is heavily bathed in radiation. I'll keep coming back to that from Jupiter, as well as its magnetic field, heavily bombarded by micrometeorites just because of its proximity to Jupiter, and it's old. Unlike Enceladus, it's at least 4 billion years old. And that's important from those parameters for habitability that I mentioned earlier. So what I've tried to do here in one slide is put together a primer on Europa. Everything that we've really learned in summary form from 1970 to about 2 weeks ago, okay, from recent data. And I will give you this at a high level, and then I'm going to go into this in depth for this part of the presentation to present our best models of Europa, how it impacts our understanding of habitability, and then where Europa Clipper comes in. So first, in the early 1970s, our surface telescope said, seems like this is a dirty snowball. Covered in water ice. It's all we could see. The images were kind of blurred. Pioneer and the Voyager probes confirmed this and saw, surprisingly, that it didn't seem like there were a lot of craters on Europa, suggesting it must be geologically active or undergoing surface remodeling. Then Galileo came along, made 12 close flybys, and gave us a lot of data, but it was rather incomplete because its antenna didn't fully extend, okay? But then we had follow-up data from Hubble, now James Webb, the Juno spacecraft, all have provided a lot of data around Europa. And this is kind of the high points. Yes, you have this relatively smooth crust, but it has these long linear features or canyons on the surface known as lineae that I'll show you, suggesting some kind of geodynamic or tectonic-like activity. It was observed that Jupiter's magnetic field was in a delicate dance with Europa and induced a magnetic field in an electrically conductive fluid interior. A really fancy way of saying they thought that Europa probably has a subsurface saline ocean. And it's that interactions with Jupiter's magnetic field that is causing Europa's field, not because it has a metallic core that is rotating and creating the field. Galileo, Juno, Hubble, James Webb all saw evidence, just like on Enceladus, for cryovolcanic activity, shooting plumes of water and grains high into space upwards of 120 miles. Yet, despite that activity, the surface ice was rock hard and really cold. So, Keck, more reanalysis of Galileo, and very recent observations from James Webb showed that a lot of these plumes on Europa, they have all those key ingredients that I mentioned before that you need for life, all the key inorganic and organic ingredients, the building blocks, as well as oxygen, CO2, ammonia, hydrogen peroxide, salt, and water vapor, all in its exosphere. It doesn't have an atmosphere. And why this is important and only recently shown is that many of these, like ammonia, hydrogen peroxide, sodium chloride, are very unstable to radiation. So the fact that we can detect quantities reproducibly suggests they're there relatively recently as a result of recent cryovolcanic activity or geologic activity. So the most conservative hypothesis that we have, really, is that Europa is an older world, geologically active. It has a thick icy crust floating on a deep subsurface ocean, and it has an induced magnetic field. So what I want to do is I want to look into this, show you this geology, because I think it's really cool, okay? And how does this affect our current model of Europa, and what does this mean for habitability? So even though Europa may be about the size of the moon, when you look at it, you don't see craters. What you see are these long linear ridges or valleys called lineae that can be several miles wide, but they extend for thousands of miles across the moon's surface, okay? Suggesting that because of some underlying geological processes, the crust is expanding, spreading apart, and then refreezing. They're not just due to some local gravitational or tidal effects from Jupiter. They're widespread. It almost looks artificial, like someone took knitting needles and knitted the surface. But you see this all over the surface of Europa. Equally interesting are these features called lenticulae, from the Latin for freckles. They're circular elliptical spots or pits. And what they're believed, and now evidence strongly supports it from Juno and again, reassessment of Galileo and James Webb's observations, is that these are areas where cryovolcanic activity has thrown up water plumes rich in mineral salts. The water obviously vaporizes into space. The mineral salts fall to the surface. They get bombarded by radioactivity and from Jupiter. And you have these spots. And again, they're not just localized here and there. They're everywhere on the surface of the moon, suggesting, quote unquote, recent geologic activity. Then you have chaos terrain. This is really cool stuff. If there's any geologists. These look like icy rafts or blocks, okay? We have chaos terrain on Earth. I've seen it firsthand in Iceland. You see these types of features where new crust is emerging like near ridges where plates are pulling apart and new materials coming up. Well, on Europa, what these are icy rafts or blocks that break apart. They undergo upheaval and rotation and tilting, and then they lateral move it, and then they freeze again, suggesting there's some kind of convective dynamic processes under the surface that is making this terrain very active. And again, it's in this terrain where we found things like ammonia and hydrogen peroxide and water vapor and sodium chloride, all of which are unstable with radiation. So we know they were deposited there relatively recently. And then lastly, the craters, or more importantly, the lack thereof. I'm showing you one. It's called Puy 2, very pretty, crater, nice rays, central impact. But on a body that's about the size of the moon, there are less than 50 craters on Europa, whereas the moon has more than 5,000. So again, just suggesting active surface remodeling. In many areas, it's estimated the crust is 30 to 180 million years old. Again, a blip in geologic time because of active geology. So if you put all of this information together, the radar, the gravimetric, the magnetographic, the photogeologic data that we have from Galileo, all the follow-up from Hubble, James Webb, the Keck telescope, and now more recently even Juno, you come with this model, or current best model of Europa. And what it suggests, it has this icy crust that's about 10 to 20 miles thick, but that crust is not uniform. We know that there's a hard, colder outer layer and an inner, more fluidic convective layer. That crust sits on top of an ocean, 40 to 60 miles deep, the topography and composition of which we don't really understand, other than we know it has salts, it's not just fresh water. And that ocean sits in direct contact with a rocky, silicate-rich mantle that is the source of a lot of the inorganic salts and minerals that we've identified in those cryovolcanic plumes. And then it has a solid metallic core, probably nickel iron, but again, it is not this core that is causing the magnetic field. It's induced because of the presumptive subsurface ocean. So what does all this mean? So this is the thing that I still can't wrap my head around. It just, you have a body the size of our moon that has twice, more than twice, all of the water we have on Earth. Just think about the size of our moon, and it has twice, believed to be twice, the amount of water we have in all the Earth's oceans. Water is life. Not saying it exists, but again. So the natural question, and you all know the answer, how does that water stay liquid? How does the ocean sustain itself? And of course, the answer is tidal frictional heating. Again, circular orbit around Jupiter, every 3.5 days, tidally locked. Enormous gravitational tugging and stretching generates huge amounts of frictional heat in Europa. And scientists believe that that heat is sufficient to keep an ocean of liquid water in the subsurface liquid, and in some areas maybe even temperate, for the age of the solar system. Not 100 million years, not maybe just a billion, the age of the solar system, or at least since Europa and its ocean were formed. And the activity of that frictional heating on the mantle is generating geologic activity, which is why we see the geology we see on the surface, the absence or scarcity of craters, this dynamic chaos terrain, the cryovolcanic activity in the lenticular, the long canyons and ridges that are expanding for thousands of miles along the surface, basically what's making Europa geologically active. But most importantly, the current best theory, not the only one, is that Europa is subject to stronger tidal forces for a longer period of time that have kept it much more geologically active than some of Jupiter's other moons, like Ganymede or like Callisto, and yes, like its much younger and much smaller cousin, Enceladus. Okay? That's why I wanted to present Enceladus to you and Europa, because they're both cool candidates. You need to consider that time and stability issue when you're talking about habitability. So where does this convection process come to play? Mostly where the ocean meets this warmer, more fluidic ice layer where water basically seeps up eventually to the surface. And this explains the cryovolcanic activity you see, these lenticulae, a lot of the other surface geology that we see on Europa. More importantly, and again, new data, this is an artist's conception, is what happens to convection in terms of the chaos terrain that I mentioned before. So the current best theory for this kind of terrain, again, modeling what we also know from Earth, is that as water seeps up through this fluidic layer, it forms these small subsurface inclusion bodies or subsurface lakes in the hard icy layer. And these bodies are very destabilizing to the icy crust. It causes them, and again, we see this, to break apart, to tilt, to rotate, to move laterally across the surface. So it is quite literally tectonics, only with water and rafts of ice rather than molten magma and crusted plates like we have on Earth. But this system is very dynamic in that we now believe that the icy top of Europa floats on the more fluidic layer and on the ocean and on the subsurface ocean. And the process is dynamic in that the entire icy crust rotates around the entire moon about every 12,000 years. So this is a very geologically dynamic world. And now the last thing that I want to show you is hydrothermal or geothermal vents. Now, I need to freeze this a second. Okay, let me see. So I said there's evidence that these exist on Enceladus. This is why I keep making these comparisons. And we believe they exist on Europa. What are these? This is Earth here, okay? These vents were first discovered in the late 1970s, early 80s, and still amaze scientists, especially astrobiologists, in that what you have deep in places like the Marianas Trench, 7 miles down, no light, extreme temperatures and pressure, you have flourishing ecosystems. Flourishing. And the base of this ecosystems are extremophilic microorganisms called chemolithoautotrophs. If you break down the word, what those organisms are doing is they are breaking down inorganic sulfur and iron from rocks and grains of rocks and dust into organic substrate. And that process is powered by the chemistry and heat gradients from these smoker vents that you saw puffing out, okay? Where really hot, high pressure, and highly acidic water, rich in minerals, is being pumped out into the water. And so you have an ecosystem. Again, it isn't just surviving, it's thriving 7+ miles down. Now, again, a caveat. These exist on Earth, and you have thriving ecosystems. We believe with a pretty degree of certainty they exist on Enceladus, and maybe 50% certainty they exist on Europa. That doesn't mean that there's life on those worlds. But again, I'm just trying to make the case that when the right conditions are present in the right time, it can give rise to life even when you would expect it should exist. So we put all this together, everything we know from all our missions, ground-based, all, Juno, Galileo, Hubble, James Webb, Keck. We believe Europa has all of the key ingredients for life as we understand it. It has twice the amount of water, the Earth's ocean. It has those essential elements that you need for life. It has a stable, sustainable energy source, tidal frictional heating, possibly also radioactive decomposition in parts of the mantle, generating heat, and maybe hydrothermal or geothermal vents. And very importantly, it has time. That ocean has been around and believed to have been tidally warmed over the age of the solar system. And that makes this a little different than its smaller, much younger cousin Enceladus. Doesn't negate this is an important candidate. It's just put this all in perspective. Now, as with anything in science, These data need to be confirmed. There's questions that remain unanswered. There's hypotheses. All the stuff that I presented to you needs to be tested and refined. All the more reason you need a Europa Clipper to generate those kind of data. And now, about a month ago, I almost had a heart attack because a paper appeared in Nature Communications where a group from the McDonald Center for Space Sciences reevaluated some data on Europa's size, the makeup of its core, the gravitational forces from Jupiter, and they concluded, yeah, Europa is geologically active, and it certainly is a really cool world. We should go investigate it, but it isn't geologically active enough to generate the tectonic activity, those hydrothermal vents, or all the other types of geodynamic activity that would be a prerequisite for life. Now, this is a minority opinion. It's out there compared to the conventional wisdom, but as most things in science, that doesn't mean we throw it away, okay? It makes it more important to have a mission like Europa Clipper to really get answers to questions, to confirm data, test our hypotheses. So this is where we are. Now we come to Europa Clipper. Again, this is the mission at a glance, okay? And I'll go into detail. If you remember nothing from this talk, Europa Clipper is the largest, most technologically advanced robotic mission and instrument package NASA has ever launched in a planetary mission. Hence, its pretty hefty price tag of $4.2 billion. Also had to overcome, or is overcoming, some enormous technical and engineering challenges getting it to the European system. So it was launched on October 14th from Kennedy Space Center, about 4 or so days late because it was a hurricane hitting the Cape at the time. And it was launched on a SpaceX Falcon Heavy lift launch vehicle. It weighed in at about 6.5 tons. And it was launched on a SpaceX vehicle for very specific reasons we'll get into later. And it is now on a 6-year, 1.8 billion mile journey, traveling at about 79,000 miles per hour to Jupiter, not Europa, Jupiter. It will arrive, again, because of the magnetic and the radiation fields, a Europa orbiter would be almost impossible. And again, I'll show you why. After 6 years, it will arrive in Jupiter around April 2030. It had a critical gravity assist last year at Mars, where we also were able to test a lot of the instruments and everything was thumbs up. The next key event is December of this year, a critical Earth gravity assist. And when it eventually gets to the Jovian system, it will make approximately 49 flybys of Europa over 3.5 years, where with each flyby, all of its instruments will be operating simultaneously for maximum data collection and to ship literally terabytes of data, through its high gain antenna back to Earth to NASA's Deep Space Network. And so the whole goal of this mission is really to assess the habitability of Europa, not really to look for life. There's a difference. Looking at a number of parameters in the surface and the subsurface. And it's also a scout. It's going to be looking for possible landing sites for a future mission, maybe in the late 2030s, depending on budget and geopolitical situations, that would actually land on Europa and autonomously drill into the subsurface. So let's just look at some of the details. Always good to put things in size. This is a big beast. See it relative to some other familiar objects. It's about 100 feet long, about 58 feet wide, so bigger than a basketball court. And that's due in huge part to these 2 giant high-efficiency solar arrays that need to be that big, that efficient to capture light at Jovian distances to power all the electronics and subsystems. So it's a big beast. And these are the solar arrays, which again, a remarkable piece of technology. These are the largest solar arrays ever launched. Now, fairness, they're not launched this way. They're launched kind of folded up. I wish I had a graphic. And fold out as an accordion, right? So these are the largest arrays. They're the most highest efficiency solar arrays made, and they're radiation hardened. They were built by Airbus in the Netherlands before being shipped to the US. And what's important, each one of these panels is about 10 square meters, so 105 or so square feet, and can generate 150 watts of power continuously at Jovian distances from the sun. But there's 10 of these panels, 5 times 2. So this craft with these high efficiency arrays can generate 1,500 watts of power continuously at Jupiter-like distances from the sun, which it has to do it continuously to power the instruments, that state-of-the-art instrument package, all the subsystems and the electronics. If the craft is pointed away from the sun, there's battery systems that are always kept charged so that the instruments and the subsystems are never at a loss for power, which is an important consideration. Again, just to give you perspective, this is Clipper without the big solar arrays. You can just see the whole instrument package. It's high gain, medium gain antennas, some of the booms, but you can just see the size of the thing relative to the technicians and engineers working. It's a big beast. And then here is an artist's conception of what it would look like fully deployed. And again, notice the size of the solar array is next to the 2 people standing there. And the reason I show you this is to point to this central feature here, where a lot of the instruments are, but this is also where the propulsion module is that was built by Goddard. So this propulsion module actually makes up about 2/3 of the body of the spacecraft, the main body, and it carries about 6,000 pounds of propellant. So monomethyl hydrazine and dinitrogen tetroxide. And more than half of that propellant will be used up when Clipper arrives in the Jovian system in 2030, because it's going to have about a 6 to 8 hour insertional burn to slow it down from 79 plus thousand miles an hour to about 10 to 15,000 miles per hour to get into orbit around Jupiter. So you can't see them, but there's about 24 bipropellant engines, each of which can generate about 27 newtons of thrust. And they're absolutely critical for attitude control, for propulsion, and for making these very fine changes in Clipper's trajectory when it gets to the European system. So what's the science objectives of the mission? Yeah, it's looking for astrobiological potential for habitability, but it's really going to be using its instruments to look at the thickness, properties of the ice shells and their interface with the ocean. It's going to do detailed analysis of the surface and subsurface composition, especially looking for non-ice material and other agents in the ice, organics and inorganics. It's going to do high-resolution assessment of the surface geology, and very importantly, it's going to want to understand what's going on in the subsurface. What the geodynamic processes that are causing all the geology we see, the absence of craters, the cryovolcanic activity, the canyons, the chaos terrain that's tectonic-like nature. And then finally, it'll be reconnaissance looking for a future landing site. So the instruments that do this, not an engineer, but I kind of really get into it, instrumentation like this, you have a panel, again, state-of-the-art instruments, both in remote and in situ. This is the most, again, sophisticated data package NASA ever put on a probe. And literally, the craft is a data gathering machine. Because as I said, when it makes a flyby, every instrument is on full blast, okay, to gather as much data as possible. And a lot of these instruments complement one another. So you have this high resolution 3D camera, get down to a resolution of about 1.5 feet from the surface. You have both a UV and infrared spectrometers that'll be looking at those cryovolcanic plumes. They'll be looking at the thin atmosphere. They'll be looking at other elements that may be on the surface for organic or inorganic signatures. You have a thermal imager looking for hotspots, literally where, maybe future eruptions of volcanic activity. And then you have something called Reason. And what that is it's 6 radio antennas that are attached to the solar arrays that are pointing down and looking for subsurface water and really looking at the interface between the ocean and the ice layers and their dynamic interactions. This is old technology. We've been using this for decades to study the subsurface properties and motions of the ice sheets under Antarctica or on top of Antarctica and Greenland. But now it's being applied to space. And then you have this complement of instruments like mass specs and SUDA that are basically mass spectrometers that are looking at surface materials. Again, the plumes, the atmosphere, dust and ice that are kicked off the surface because, again, Europa is constantly bombarded by micrometeorites, given where it is relative to Jupiter. Certainly, you need a magnetometer. You want to understand that induced magnetic field and what are the properties of the ocean that are causing it. Because you're getting bombarded with so much radiation, Faraday cups, you're looking for charged particles and capturing them and studying them off the surface. And then this instrument is really important, especially in view of that rather contentious publication. It's going to really look at and measure the magnitude of tidal heating by Jupiter. Not just impact on the ocean, but on the ice shelves and especially down below the mantle to know whether there is a lot of active geothermal activity going on the moon. So this is the whole package. And now this is just showing it in relief. Now this is the key part, and we're almost at the end. The whole issue with why this mission is so challenging, technically and from an engineering standpoint, and I've alluded to it multiple times, is because Europa lies within close proximity to Jupiter's enormous magnetic and punishing radiation environment, probably the second most punishing radiation environment next to that of the sun, okay? When the magnetic field of Jupiter is oscillating, it's not only interacting with Europa, but it acts like a linear accelerator or a particle accelerator, bombarding Europa and the innermost moon Io with enormous amounts of high energy particles. So this is a hellish environment from a magnetic standpoint and a high energy radiation standpoint. This is why a Europa orbiter would be essentially impossible, because the instruments would have fried very quickly from radiation damage. And to shield them all sufficiently would have added so much mass and cost that the mission would have been prohibitive. It also is the reason why I mentioned the JUICE mission by the European Space Agency, because they're not going really to Europa, just 2 flybys. Ganymede, Callisto are way out here. It's not that they don't get hit by radiation or Jupiter's magnetic field, but much, much weaker effects than the kind of bombardment that Europa is getting. This is what made this mission so expensive and so challenging. So kudos to your tax dollars and NASA engineers, because they overcame this problem by multiple approaches, but there's 4 that are worth saying. First was shielding. They prepared an aluminum, titanium, zinc shielding at great cost and mass, just to shield the most sensitive electronics and subsystems from acute radiation. Again, they couldn't shield the whole craft. It would be too heavy and cost too much, but that helped. The second thing, which just blows my mind, the instruments were designed to have self-annealing properties. So at the risk of anthropomorphizing machinery, basically what this means, by having constant or continuous power and being able to pulse that, it allows the instruments to repair or heal from acute radiation damage and stay healthy. Think of it, if you had an abrasion on your skin, or, you probably don't need medical care. You'll heal it, right? All by yourself. Similar concept here, a self-healing system of the instrumentation, which is extraordinary. The third thing, ingenious orbital dynamics. And I'll show you this in the next slide or two. The engineers designed various orbital trajectories of Clipper so that it minimizes the time the craft is spending in the most damaging radiation areas around you, while maximizing its data collection from all those instruments that are operating simultaneously. Okay? And then the last feature is really incredible advances in data compression technology and error correction technologies and the integration of those two. What do I mean? In the course of the mission, Clipper will send back terabits of data with its high gain antenna, narrow focus beam to NASA Deep Space Networks. Sending that data back, it's not only the distances involved and the 30+ minutes to send a signal, but you need to send those signals to a heavy radiation environment. And as you probably know, radiation doesn't just damage instruments and electronics, it decays signals. So the advances in integration of data compression and error correction were to guarantee that the data that was being sent back would be at the highest fidelity. So those are just some of like the engineering or technical feats that had to be overcome. And it's kind of shown here in a cartoon form. When it gets to the European system or the Jovian system, again, Clipper will make about 49 flybys over its 3.5-year mission. It'll come as close as 16 miles to the surface of Europa, and as far as about 1,670. And every flyby that it makes, it'll spend less than 24 hours close to Europa, less. All instruments operating full capacity, and then it zips out. And 2 to 3 weeks later, it repeats another flyby. And 7 to 10 days after each flyby, it dumps all of the data that it gathered from its full instrument package back to Earth. And it needs to do that through its high gain antenna, just in the event if there was a critical mission failure, you only lose the data from the last flyby, not the whole mission. But again, this whole iterative process is really designed with 3 goals in mind. Minimize time in a heavy radiation environment, maximize data collection, and maximize the integrity and the fidelity of the huge quantities of data that you're sending back. Now, little graphic showing you how the spacecraft enters the Galilean moon system. We'll add some caffeine. If you speed it up, the key point here is, or a key feature of the mission is that Clipper will get gravity assists from Europa itself and Ganymede and Callisto to change its orbital trajectory ever so slightly. So there's a different closest approach point to Europa with each flyby. Again, to maximize data collection, minimize radiation exposure. And when you follow this out over 3.5 years at approximately 49 flybys, you get this very visual, artistic rendering called an orbital pedal plot that kind of shows you visually just the complexity of how the engineers had to calculate these different trajectories and alter them ever so slightly to accomplish the mission objectives here. So again, really kudos to the people who worked on this project. It's pretty extraordinary. Now, even with all the technology, even with all the engineering, this is still a super high risk mission. Super high risk. Possible high gain, but super high risk. And this little graphic shows you, again, it's an orbital pedal plot, but from a different angle. And you got a little Geiger counter here ticking away every time the craft makes a flyby. Again, remember all the precautions I told you to minimize radiation exposure. Even with that, over a 3.5-year mission, the total accumulated radiation is just over 2.8 million rads. That's several million X-rays. And again, this is with all the precautions we took. So by no means is this like a walk in the park or a sure thing. This is a really high risk mission. So far, so good. And now, last few minutes, I want to shift to what I told you about ambassadors for humanity. Ever since the earliest days of our probes, any probes that we sent, especially into deep space, you always wanted to convey some messaging on them, either for future generations of humanity, thousands or tens of thousands of years from now, if they should encounter this probe, or, no puns intended here, in the eventuality that one of these probes should leave the solar system, which again is a non-zero possibility, and somehow millennia from now be encountered by an intelligent civilization, should one be up. We wanted to send some message about who we are, what we're about, where we're from, and that our intentions on sending this piece of hardware into your neighborhood are benevolent. So the earliest example of this, many of you probably old enough to remember this, was quite controversial in the 1970s, was the gold anodized aluminum plaque on the Pioneer missions. We had naked man and woman not holding hands, so it couldn't be construed as they were one being, in a gesture of friendship. basically had information of when this mission was launched, from where in our solar system. It had spectral lines for hydrogen and hydroxyl, again, water and water, just to send a message. Should anyone receive this? The Voyager probes, rightly so, took this many quanta higher in terms of sophistication. Each of them had a 12-inch gold-plated copper phonograph record encased in aluminum. And on this record were sounds from the Earth, images from the Earth, messages from notable people, even details of the mission, all translated into a mathematics-based code and physically etched into the record. And they even attached a stylus and little instructions as to how to listen to read the record, all just in case someone were to get this and have the mathematics wherewithal to be able to deconstruct this, again, to be able to tell people our intentions are benevolent. So it really shouldn't surprise you that a mission like Europa Clipper that's going to the outer solar system, whose goal is to look for habitability parameters and maybe even find some remote evidence of life, wouldn't have had a similar kind of approach. And so the mission had the message in a bottle campaign where they invited the public to submit your name. That would be attached on a microchip that would be on a plate, a tantalum metal plate, along with other mission information and details that I'll show you in a moment, for this journey to Europa. Okay, and 2.6 million people, myself included, sent their name and have it attached to this little microchip. And this metal plate, remember I told you they shielded the most sensitive electronics? This tantalum metal plate seals that ball. Okay, so anyone, it would be impossible not to see this plate. And this is what this plate looks like. And it's really quite intriguing. So in addition to the chip with all the names, it has some details about the mission. It has a beautiful poem written by poet laureate Ada Lemon about Europa that I'll show you in a moment. It has the Drake equation that I'm sure everybody knows, equation to predict the probability of an intelligent spacefaring civilization living elsewhere in the universe. Here, hydrogen and hydroxy radio waves, again, pointing to water, always to water. And you have a picture of this guy, Ruggeri, now deceased. He is a pioneering planetary geologist. He did some of the seminal photogeologic surveys of Europa from the Galileo data. So all of this is encountered on this one plate. And on this opposite plate, you have the words for water in 104 different languages in the form of human voices engraved as waveforms. So there's a lot of information on this plate just in case. And just to show you, this is the poem in praise of Europa. And it's appropriate not just for Europa, but really a mission to any icy moon. And I won't read it, except these last 5 lines are pretty telling. I think they express the sentiments of the 4,000 or so people that have worked on this mission since it was conceived about 11 years ago, and the 1,000 or so scientists and engineers that still do. And it's not darkness that unites us, not the cold distance of space, but the offering of water, each drop of rain, each rivulet, each pulse, each vein. O second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark. If ET reads that and it can understand it, I don't know how they couldn't know that our intentions are benevolent. But anyway, so that's where we are. The mission is 16 months in. The next critical event is December of this year for Earth gravity assist, but so far everything is operating swimmingly, actually. You can follow this on any number of different social media platforms. And you're going to have this presentation archived. This QR code, if you scan it, you will find more than you ever wanted to know about this mission or Europa, and any kind of activities or events that you can participate in, or your kids can participate in. It'll take you to many sites. So to conclude, I'm an optimist, okay? But I believe that in the 2030s and probably the next 25 years, it'll be an unprecedented period of discovery that we probably haven't seen, well, we've never seen, frankly, okay? To really address the question of habitability and potentially even find some clear signs of microbial life elsewhere in the solar system. Both Europa Clipper and the JUICE missions, if they're successful, will be pumping out huge amounts of data in the 2030s. We may also send a lander to Europa in the end of the 2030s. Already mentioned the missions planned or in conceptual stage for Enceladus, the NASA's Orbilander mission. China and the ESA have mission concepts. Even with all the mess that we have in the last 6 months or so regarding funding for NASA, NASA gave approval to build a nuclear-powered quadricopter that's going to be sent to Saturn's moon Titan. It'll be launched in 2028, get there in round 34. This thing will be automated, remote controlled, be able to take off vertically, go from place to place, and it will have quite a sensitive instrument package to look at that prebiotic environment on Titan to assess the subsurface ocean. So the point is, the world, NASA, ESA, Chinese Space Agency, who knows by then, others, we're taking multiple shots on goal. So have to believe with this technology, this engineering, we're going to get some definitive answers to this question. So sorry if I went over there, I apologize, but that was all I had for you.
Other questions?
Yes.
Oh, can I get that QR code back up?
Sure. Yes, or we can, the presentation you have.
It's archived, yeah.
That's archived. You can see.
But you want to just flip back to it? Is that cool?
Yeah, sure. Take a photo.
Yeah. There we go.
Yes.
It's kind of two questions sort of related. That it looks as if the assumption that of finding possible life, that life would be anchored, if that's the word, on the, whatever you want to call it, soil, mineral substrate. Is that what, or would that, is there a thinking that there's like possibility of free floating microlife in the oceans themselves?
That's the conventional wisdom. And again,
Okay.
that's just hypothesis.
Sure.
Okay, it's just hypothesis. But you're putting everything together based on the models we know and everything that we know from Earth and what our concept of life, that would be the concept. And whether it's on Enceladus or whether it's in Europa, it would be in the, certainly not going to be in the surface. It would be in the oceans. And if there are hydrothermal vents, conceivably, and again, I have to make all these caveats, it could be just like in the depths of our oceans, you could have active ecosystems near those hydrothermal vents because you have everything you need. You have heat source, you have energy sources, you have all the inorganics you need for life to
Yeah,
thrive.
that's what it looked like. The assumption is that that's where
Yeah.
life would most likely be.
Yes.
You have these moons that are relatively small, containing all this water.
Mhm.
Where'd the water come from?
Good question. I could speculate on that, but I don't want to give you nonsense. I'm not sure that's 100% understood, other than it's been there, at least in the case of Europa, since the start of the solar system. So it's kind of water from origin. It's not believed that this water was somehow deposited on the surface from comets or asteroids. But exactly the process, I honestly don't know. And I'm not sure anyone, they may speculate, but they know for sure. And you also have to know, I hope I said this, presumptive oceans, okay? Presumptive. Nobody's ever gone there, drilled down and said, wow, we found water, right? I mean, we're assuming based on all this cryovolcanic activity. Certainly Enceladus, certainly Europa have oceans, Ganymede. But a moon like Callisto and some of these others that have low percentages of water, that gets much more gray. Much more gray. But it's a really good question. And I 100% can't give you a clear answer. Yes.
The Voyager 1 and 2, they were nuclear powered.
Good point. they have RTGs, radioisotopic thermal generators, okay? This craft does not, by design.
Yeah, I just wondered why.
So early on, mission papers came out, should we put an RTG on Europa Clipper? Because again, it has this sophisticated instrument package, you're jogging distances away, you need a backup power source to the solar arrays. The conclusion of that was it was not cost effective and it was not practical. And something talked with a couple of people at JPL, they said that they think the real reason is this. You didn't want to have the possibility that a craft with a plutonium power source may crash into Europa or into Ganymede or one of the, if it goes into Jupiter, that's fine. But you didn't want to do that because you're looking for habitability and maybe some, you don't want to have a nuclear power source. And so push for high efficiency solar.
Now, Jupiter has a magnetic field, I understand. Now, do the other planets have a radioactive fields as well,
Other,
besides Jupiter? I mean, why is Jupiter so radioactive?
well,
I mean,
again, we have a magnetic field as well. Our magnetic field is about 25,000 times less powerful than Jupiter. It's a question of mass. Jupiter's magnetic field has issues of it itself. But again, remember I said when the field rotates, it acts like a particle accelerator. So that's why several of these closer moons like Europa and Io are getting bombarded with high energy particles. The moons that are further out, it's not that they're immune from that, but it's much less intensity. And that's a unique feature to Jupiter that some of the other planets just don't have that degree. It's a matter of degree. But that really has challenged the whole design of the mission. Yes.
Just for frame of reference, so on Earth's surface, we're shielded by our atmosphere from the solar rays, but we as humans are getting about 0.3 rem per year from the sun. The surface of Io, you're getting 3,600 rem per day.
Io, yes.
So you, like a human, just from the radiation, you'd be dead in a few hours.
Right. And a human being could never, quote, walk on the surface of Europa either, because the radiation is too much, or you'd probably get pelted by micrometeorites. So all the action is subsurface in all of these moons. It's a really good point. Yes.
Sorry for the moon.
No.
Since you talked about walking on Europa.
Oh, God.
If anybody's seen the movie Europa, so I guess that's not viable. I would say.
Explain the premise of the movie, because I may be confused.
So it was kind of an indie film, and it was a privately funded mission to Europa.
Okay.
And there's a scene where they kind of crash land on the surface, but they at first. And then one of the scientists actually goes out to try to collect samples from the ice. And they did show, like, she's walking around out there and they're showing the dosimeters going.
Yeah.
Okay, come on back.
Yeah, I never saw that, but I've heard about that though. It just is just an aside. I don't know if any of you are Arthur C. Clarke fans. All right. But I'm blanking what book it was, but he even mentioned, again, it's sci-fi. He always said we should not try to land on Europa.
2010.
We don't want to disturb Europa. We could go to other places, because even then he thought that given what we knew, which was much less, something special about Europa. We didn't know as much about Enceladus at the time. There was something special about Europa. Let's be gentle with it, kind of thing. So again, yes. I thought it was the third.
Second.
It's the second one?
Yeah, when you talked about China going to Europa, it reminded me of when they, in that book where they stopped there for fuel.
Yes,
Yeah.
yes, exactly. The fiction's becoming reality. So, yeah.
Yeah,
Yes.
remember that. On Earth, we've seen all life in these extreme environments, heat and chemistry and all of that.
something like the
Life is adaptable. I imagine it did not initiate in those extreme conditions, but maybe in more some friendly kinds of environments to begin with, and then adapted to those extremes. Is there any indication on Europa and Enceladus that conditions might have been more friendly to let life get initiated and then adapt to the extremes.
It's kind of a chicken and egg question, so it's a little hard to answer. So so again, let me say, we don't know if there's any kind of life on Europa or Enceladus, but you have you have the necessary ingredients for life to possibly occur. So when you say adapt, okay, let me answer this way. There's an exobiologist who works for NASA, and his premise is we shouldn't be asking, is this world habitable or not? Does this world have life or not? So we should be asking, it's kind of what I said in one of my slides, how much time has progressed to allow complex organic chemical evolution to occur from really simple building blocks to more advanced intermediates like carboxylic acids and amino acids and nucleosides to complex self-replicating molecules, not life. So proteins, large change hydrocarbons that have the means primitive, albeit primitive, that they can replicate. And then life, simple life is several steps beyond that. So it's not so much an adaptation as much as the time under the right set of circumstances for certain key events to happen so that you have a sustained self-replicating system. Does that make sense? It's not quite the same as adaptation. It's just giving time for molecular evolution in this case to take place.
And are those the processes that would have happened in the early Earth?
Yes.
At the beginning of
That's what we believe.
how life
Yes.
took.
Yeah, I'm not taking any religious stance here. Okay, don't judge me. But yes, and in fact, that's one reason why there's so much interest in going to Titan. Not because like we're going to find people walk around on Titan, but because it resembles the atmosphere, a lot of the chemistry of what we believe pre-life, pre-biotic Earth had. And so it's kind of an origins of life laboratory potentially, which is not the same as Europa or Enceladus, where there could be simple life. You see the difference? Yeah. So, but yeah, that's the best of our knowledge. That's how things progressed here. And again, I don't want to get into an evolution debate or anything. I'm not trying. You get my point. It's and all we can do is base all of our hypotheses and ideas have to be modeled on something. What's our model? Our model is here. What we know of our past and what we know now, and we know how things are changing. And again, how organisms can survive under really extreme conditions and not just survive but thrive. That's how we're modeling all these things based on what we know so far. And it's an incomplete story. Yes, anybody else?
All right, well, let's. And as a reminder, as always, keep an eye on the groups.io and please join us for some refreshments in the library.
Mr. Diana?
Yeah, thanks to Diana.